Will NASA's Sunbeam drive soon take us to distant star systems? Due to the immense distances in space, the dream of interstellar travel has long seemed unattainable. However, experts have now developed a revolutionary concept that could finally make the leap to far-off worlds a reality. The Alpha Centauri star system, just 4.34 light-years away, may seem unreachable with our current technology. But with new propulsion innovations, a probe could reach it in just 40 years. The foundation of this new Sunbeam drive appears simple. Space gas stations are non-existent, so what if we supplied a spacecraft with the necessary energy externally? That's exactly what NASA's new concept envisions. The spacecraft will not carry its own fuel but will instead be powered by an external platform supplying energy through a particle beam. This method allows for incredible speed increases, far beyond anything previously possible. Recently, the Parker Solar Probe became the fastest man-made object ever, reaching 692,000 kilometers per hour as it approached the Sun. While impressive, this pales in comparison to the speed of light, estimated at around 1.08 billion kilometers per hour. With Sunbeam, it's possible to accelerate a probe to 10% of this speed, meaning it could travel at 100 million kilometers per hour. How is this possible? The answer lies in relativistic electron beams. Electrons accelerated close to the speed of light generate enough energy to propel a 1,000 kilograms probe across interstellar distances. If this approach is realized, Alpha Centauri will no longer be thousands of travel years away, but just 40 years. This is particularly exciting from a research perspective because the Alpha Centauri system includes Proxima Centauri, which may host a habitable planet, Proxima b. To understand the vast distances in space, consider the Voyager probes. Since their launch in 1977, Voyager 1 and 2 have traveled an incredible 24.81 and 20.74 billion kilometers from the Sun, respectively. However, even at speeds of 61,000 kilometers per hour, they have not yet covered a single light day. In contrast, Sunbeam's potential 100 million kilometers per hour speed makes Voyager's journey seem like a snail's pace. How does Sunbeam technology work? The core component is the solar station, a fixed platform positioned near the Sun. It remains stable using light pressure and solar magnetic fields while firing a high-energy electron beam at the probe. A massive solar shield protects the spacecraft, and as the beam strikes it, energy is transferred, continuously accelerating the spacecraft without requiring onboard fuel. The longer the beam acts on the probe, the greater the speed boost. But won't the electrons eventually scatter into space? Surprisingly, no. When electrons travel at relativistic speeds, near the speed of light, they exhibit an effect called pinch due to time dilation. This prevents them from spreading apart, keeping the beam stable and focused over vast distances. #advantages over breakthrough starshot. The idea of using an external beam for propulsion isn't new. In 2016, the Breakthrough Starshot project, involving renowned scientists like Stephen Hawking and Freeman Dyson, proposed a similar idea. However, while Sunbeam aims to propel a 1,000-kilogram spacecraft, Breakthrough Starshot relies on tiny gram-scale probes with light sails, powered by a massive array of lasers. Starshot's concept requires an enormous 100-gigawatt laser array focused on a small sail from 20 million kilometers away. Sunbeam, on the other hand, offers a more feasible approach, potentially enabling the launch of a fully functional research probe to Alpha Centauri. This would allow us to determine firsthand whether Proxima b is truly habitable. Though Proxima b is likely tidally locked, meaning one side faces perpetual daylight while the other remains in eternal darkness, a narrow twilight zone between these extremes could harbor liquid water. If life exists there, discovering it would be the greatest astronomical breakthrough in history. #challenges to overcome. Despite its promise, several challenges remain before Sunbeam can become a reality. The biggest hurdle is energy supply. The relativistic electron beam must first be generated, and then it must be precisely aligned with the probe over interstellar distances. Even the slightest deviation could cause the beam to miss its target, dooming the mission. Additionally, as the beam travels further, maintaining its effectiveness requires increasing amounts of energy. Since the solar station will be positioned near the sun, it must be made of materials that can withstand extreme heat and radiation. Fortunately, previous advancements suggest these challenges are not insurmountable. The Large Hadron Collider at CERN already produces beams with higher energy levels than those needed for sunbeam. Furthermore, modern particle accelerator guidance systems could provide the necessary precision for interstellar targeting. The Parker Solar Probe has already demonstrated that spacecraft materials can endure extreme conditions near the sun. In terms of power generation, scientists propose using thermoelectric generators to convert the sun's intense heat into electricity. However, large-scale solar power plants in deep space remain technologically unfeasible for now. ### The future of sunbeam. Currently, sunbeam exists only on paper, and even the most optimistic estimates suggest it will take at least 20 years before a prototype is launched. Beyond technical development, funding remains a major question. Developing a brand new propulsion system could cost several $billion, making it unlikely that NASA will fund it alone. A more realistic approach would involve collaboration between multiple space agencies, as well as financial support from private investors. While patience is required, sunbeam is far from an impossibility. If history has taught us anything, it's that technological progress can be rapid and unpredictable. Just 66 years separated the Wright brothers' first powered flight in 1903 from Neil Armstrong's moon landing in 1969. With that in mind, who's to say that the first interstellar probe couldn't be launched within our lifetime?